so that what gives a balanced machine when we have 1 bit of I/O, sequential I/O per second per every instruction. And at that point in 2005, the NSF asked for a white paper about petascale computing, and Jim and Gordon and I wrote down a short paper, which we eventually published also, about how would such a machine look like if it had the perfect Amdahl balance. And it's interesting, we actually had a line about exascale. So what would be if we had exa operations per second, and then this would require an exabyte of memory according to Amdahl's laws. It would also have a bytes per second. It would have 100 petabytes per second I/O speed to be Amdahl scaling. And in order to do this, if we assume that regular hard disks make up the I/O, we would need with 100 megabytes per second disks, we would need actually 1 billion hard disks for such a machine to be Amdahl balanced. So this is clearly out of the question. And sorry? Yeah, but a spinning hard disk still, you know, if you buy a Seagate drive, you can maybe get 120 megabytes a second or so. It's not getting much faster. So even the solid state? No, solid state disk is different. But with solid state disks, you won't get actually you won't get much storage capacity. So this is not a system to build, but just put it in proportion. Okay, and by the way. So if we needed kind of 100 times the RAM for the hard disk, that would still mean 100 exabytes. Not even Google has that much right now. So it's kind of sobering. So at that time, we also computed Amdahl numbers. So they basically take the normal sequential I/O in bits per second and roughly count the clock rate of the processors for different types of machines. And so this is this Amdahl number, and an Amdahl balanced machine would have an Amdahl number of about 1. Okay, so and the Beowulf cluster, the typical Beowulf cluster would have an Amdahl number of about 0.08. A power desktop with fast disks would have about 0.2. Then this was SC1 was, I believe, whatever was published about the Lawrence Berkeley lab that was a Blue Gene. So it had an Amdahl number of 0.001, and this was the Pittsburgh Cray XT3 at that time. And so we set out to build a machine out of Dell servers where we tried to maximize from commodity components the Amdahl number, and we were able to build a machine with about a half, to use it mostly for distributed database services. One can argue, and people have argued over the years, that with cache hierarchies, the Amdahl number is irrelevant. However, it turns out that eBay is running a system with an Amdahl number of 0.85. And IBM built a flash attachment or a flash version of the blade for their Blue Gene Q, and that has an Amdahl number also of about 0.8, where they put a bunch of flash on board of the Blue Gene Q card. But one can also, so these are actually the different machines. So this was the kind of the blue triangle is the Graywolf servers that we use for the Sloan survey. The green is a Beowulf cluster, the Amdahl number. And these are the 2 supercomputers mentioned in this article. And these are also data, one can also ask the Amdahl number of data sets. So take a data set and either how much cycles did we spend on querying the data or how much CPU did we spend on actually generating simulations. And I asked Volker for some numbers, and Piero gave me some numbers about Via Lactea. And basically what is remarkable, how these simulations run on supercomputers are kind of very far away from what the hardware can produce on those machines, whereas on the database queries, we are kind of saturating the hardware. So I was puzzled a little bit until I actually looked at the data sizes. And it does look like basically everybody got stuck. This was a few years back. Everybody was stuck between 10 and 100 terabytes. So in a sense, in the simulations, wouldn't it have been nice to use more of the I/O speed of the machine and generate a petabyte of the simulation and many more time steps? And it would have led to more interesting science. But we were limited. There was simply, and this is still by and large present today, so it's no miracle that the Millennium Exascale only put out 4 snapshots of the dark matter particles because they ran out of this space. Anyway, so I had the privilege to work with Jim, and he codified a bunch of laws of data engineering. And one of the first was that scientific computing is increasingly revolving around data. And I think it is true even in the simulation context. And so this is what I would like to focus on today. His second law was that we need a scale-out solution. Instead of building a data supercomputer, we really should buy basically cheap machines, scaled down and out. And essentially, this is what Google and Facebook are doing with a cloud solution. Once we have too much data to move around, we have to take the analysis to the data. But this is a very important, the 20 queries is, I think, one of the most profound of these, where he said that, okay, instead of writing down a 500-page requirements document, give me the 20 most important questions you want to ask from the data. And then when I first met him, okay, I said, come on. So I want to ask anything and everything. This is what science is about. And he said, okay, just give me your 20 questions. And I wrote the first 5 down really quickly. Next 5, I had to scratch my head. And after I said, okay, I have to go down and think some more. So not all the questions we want to ask from the data are equal. And some we want to ask every day, and others we also maybe only want to ask once a year. And so that taught me some humility. Anyway, so HPC simulations are getting increasingly important. So it's not just the instruments which generate big data, but some of the biggest supercomputer simulations are now really approaching or exceeding petabytes, especially if we had the storage. And this is ranging over a wide range of scales from supernovae, turbulence, and even now in systems biology, brain modeling, people are starting to generate bigger and bigger data sets. At the same time, as the machines are getting more and more expensive, there are fewer codes which really scale to 300,000 and million and soon a billion cores. So this means that there will be also these machines are getting, as they are getting more and more expensive, there's a smaller and smaller fraction of the community who can use this efficiently. But at the same time, in order to support this, one needs the community's support to fund the machines. And so it is important to increase somehow the footprint of these simulations. And it is not going to be that we will have tens and hundreds of thousands of people running such simulations. The best way to accomplish is to make some of the most important simulations public and come up with a metaphor and a way for the community to actually use these simulations. And this is what I would like to focus. How can we turn this into interactive numerical laboratories where people can go in and play with the data, just like we are now getting used to playing with observational data? This creates a whole bunch of new challenges. First of all, it's clear that the secondary reuse of the data is not going to be at the supercomputers because they are architected to do different things. The Amdahl numbers are really for the number crunching and not for the supporting the database queries or whatever. So how do we first of all move the petabytes of data from where they are generated to where they are going to be served up? How do we look at it? So for example, how do we do visualizations with many petabytes? Today, again, streaming it into our GPUs and workstations is fine, but this is already I/O limited on a terabyte scale, not to mention the petabyte scale. How do we interface with it? So what is the metaphor? Today, we download all the files that work with tens of gigabytes. It barely works with a terabyte, and it's surely not going to work with petabytes or exabytes. How do we do the analysis, and what kinds of analysis patterns do we see? So what are the 20 questions we want to ask from these very large data sets? And then what are the architectures that can support these questions? Starting with the transfer, Pierre already mentioned this. So at some point in time, when the Silver River was running on the Jaguar, there came an email to Mike Coolan that, okay, we have 2 weeks to take the data because then we are wiping our disks. This was 146 terabytes. And okay, so we said, fine, we have a 10 gig line to Chicago, and Chicago has a 10 gig line into Oak Ridge. However, this was about a week after Oak Ridge had a major security violation. So they were buttoned down. And so then we tried transfer data out. It was like 5 megabytes per second. So that didn't work well. And so we talked to Joe Mambretti, who's running Starlight. He called the head of cybersecurity at Oak Ridge, and eventually they poked a hole on the firewall. But then it was 10 gig was not routable at the time. So what we could do is to copy then things over to disk in Chicago and then copy the disks then over to Baltimore in 2 steps manually. So it was touch and go, but in the end, so this is when Mike went to sleep every once in a while. So it had to be done manually, so it was by far from easy, although a task that should have been very, very trivial.
You couldn't have had someone physically bring a...
Well, 150 terabyte at the time was kind of, this was a time of 750 gig disks. That's actually a lot of time. By the time you mount those disks, etc., you copy those disks, it's actually, and 150 or 200 disks is actually not, doesn't quite fit in a suitcase. So I would say that works on a 10 terabyte scale. So SneakerNet works on 10 disks, and I have done it quite a lot of times. Okay, so what is emerging that in the usage scenarios of big data, there is a whole variety, a whole spectrum of use cases. So typically what we mostly do today is on-the-fly analysis. So do much of the analysis while the simulation is running and extract as many things as we can. But here the disadvantage, and basically this means that the analysis is immediate. We don't keep any data except for the extracted and the aggregated things. This has the advantage that it doesn't require much on the storage. At the same time, we can't go back. So if we don't get it right the first time, it's gone. Then there's the private reuse when we actually store some of the snapshots. This is the second kind of popular modus operandi today, that it goes into scratch disks, and we keep it for a couple of weeks, maybe to a month. At that point, then we can go back to some of the snapshots that we stored and basically do the analysis and then wipe the data out. Public reuse is when we actually make the files available, and some simulations have done this. And this works, again, up to a few terabytes of aggregate data volume, when people have to download the files and then they read basically the file formats on their own machines and so on. This doesn't require that much of an investment other than kind of a stable file server. But once you start to create public service portals where you add services on top of the data and you expose the data through a services interface, this also means that you started to invest serious software development efforts into developing those services. So if you did that, you don't want to take the data offline, basically very shortly. So then you want to recoup your investment. And then there is what happens with the archival and curation of data sets that really exist over a long time. And so far, I know really only of the Millennium, which is in that category where we have to start to worry about. It is now almost, it's 8 years old data, and it is still being used very, very heavily. So it's almost a decade old. Anyway, what is emerging, though, that these lower tiers are starting to become quite different from the traditional supercomputer usage pattern. And of course, there is a vacuum. So right now, there are very few people and organizations which pick up, I think, this problem. So there is an opportunity to create a network of data resources, really. So there is really a vacuum, and there is a need for this. So I would like to show 2 use cases, how we try to overcome on a small scale some of these challenges. First is turbulence. This kind of grew out of an accident. So I was on a thesis committee with Charles Menable, and they were running a simulation, a Fourier code turbulence simulation, 1,000 cube, on a Beowulf cluster, and they were putting in Lagrangian particles, which was running on top of the simulation, and they were doing particle tracking to extract statistics on the trajectories. And the problem was that the particles, due to the chaotic nature of the flow, never ended up in the place where they wanted it to be. And every run took 2 weeks, and it was not converging, and his student had to do the thesis. We were already doing Sloan at the time. So Charles asked me, okay, so if we stored 1,000 time steps, that would be about 30 terabytes. Can we actually do it? And we had the disk space, so we said, okay, let's try it. So we run 1,000 cube times 1,000 time steps. It's actually 1,000 snapshots every 10th time step, and then basically put it in a database. I will And we came up with a really nice metaphor, I think. So instead of forcing people to download the files, we said, if you want to trace a particle, why don't we do the following? This was at the time when the movie Twister was around. So let's play Twister. So take your laptop, shoot a bunch of particles into the simulation. We extract a little kernel at the particle position, do the eighth order Lagrangian interpolation of the velocity, and return the velocity to the laptop. And then you do whatever you want with it. And it's a simple and flexible interface because you can lay down the particles in a loop around the vortex to measure the vorticity. You can do a two-dimensional cross-section. You can do a line. Or actually, you can take the equations of motion that you want and you can integrate your particle along your laptop. So after a time step, you again request the updated velocity field and so on. Worked like a charm. And question was, why a database? Why not just a file storage? Because it turns out when you want to extract an 8 neighborhood to do the 8-point interpolation, that's a very different pattern than as if you wanted to actually sweep in the whole cube. And so here, if we have a good spatial index, we can immediately go to that epsilon neighborhood. And if it is stored cleverly along a space filling curve, like Nick mentioned yesterday, we basically don't have to deal with the strides. So we have a coherent memory access or disk access. So storing it along a space filling curve in a database is maximally sequential. And of course, yes, one can build index files and write the engine on top of it on flat files, but then I would call it a database. Basically, then we are writing a database. There is another advantage. SQL is a declarative language. So once you scale out, the I/O of a distributed system starts to become pretty complicated. And I think we already spent decades to understand how do we manage, for example, the memory, CPUs, and networks on the supercomputers. But it is clear that even for Google, it was a difficult task to actually write a complex I/O scheduler. This is why they came up with MapReduce, which is basically just doing a round-robin sequential scan of all the disks, because that's a predictable pattern. But in a relational database, people have also spent decades in figuring out that how do you come up with the clever query plans of all the different ways you can access the data, which is the most efficient. And the users are isolated through the use of a declarative language. And in this case, when we have these virtual sensors, the users don't really care whether it's 30 terabytes behind it or 30 petabytes behind it. All they care that the particle velocities come back fast. So they are isolated. But what we learned the hard way, loading data into database is a pain, generally. So much, much slower than just copying files into a file system. In particular, because the data is organized into a set of linked pages, and the pages are typically 8 kilobytes. So when you take a terabyte and break it up into 8 kilobytes and build up a doubly linked list of those and a B tree on top of it, it takes time. So it would be nice to get around this. Anyway, so this is a typical usage, for example, of the turbulence data. So you can put in particles which are along this rectangular line, and then instead of integrating them forward, which is easy, you could do it while the simulation is running. You can actually run time backwards. And this is not easily done in a dissipative simulation. So you get features that you don't have otherwise. And the descent philosophies were again using space filling curves. We ended up using for the turbulence the Z-curve or the Morton curve, where the space filling curve is coming from the bit interleave of the discretized X, Ys, and Zs. Here the advantage compared to the usual Peano-Hilbert curve that everybody uses in cosmology, that there is a bit twiddling formula how you can translate the X, Y, Z into the hash and backwards. So it runs, so you have a direct mapping function instead of calling a function recursively, like you have to do it for the Peano-Hilbert. At the same time, the Peano-Hilbert has better clustering properties, so there's a trade-off. Okay. Anyway, the other missing piece was that it would be nice to store actually, so that we don't go down with the curve, with the space filling curve, all the way down to the root level, to the particle level or cell level. But we basically keep the smallest cell size roughly at the size of the interpolation kernel, which was an 8 cube. And so we built, so one of our students built an extended data type for a database where we can store a multidimensional array as a primitive database data type. And we added all sorts of MATLAB features so we can do array manipulations on it, wrapped into SQL functions. And then this is kind of the web services API. So there is a set of server nodes, and then there is an access server and scheduler, and then all the users come in through a web services portal. Anyway, this is a typical daily use. So on a typical day, we deliver about 100 million points to the world. And it's being used from all over the world. And in 2011, we already exceeded 100 billion points on the Turbulence database that delivered to everywhere. So recently, we started out with a 30 terabyte isotropic turbulence. Then we did a 50 terabyte MHD. And this is a paper coming out of this MHD simulation that appeared in Nature a few months ago. Here we did basically particle backtracking, but with a stochastic equation of motion. So all the particles started out here, and this is the backwards trajectory. And integrated backwards in every time step, we added a stochastic term to the force. And then we looked at the initial conditions, all the way back to the beginning of the simulation. Then we looked at the magnetic field at that initial condition and propagated backwards on the trajectory, the magnetic field, and then looked at how all these magnetic fields added up to the field actually computed. And it turned out this was a conjecture by Richardson back in the 1920s, 30s, and apparently it works like a charm. So it made into a Nature paper. This would not have been possible basically any other way. So, but at the same time, if we want to do a visualization, the space filling curve is a pain in the butt because the data is now not organized in a coherent fashion for the visualization. So this is when we were streaming the data, when we were streaming the data into the turbulence, into a GPU card directly from the database. And we actually issued a database query, and it delivered the 8 cubes into the GPU, and then we used the GPU's memory bandwidth to put them back into place. So we used the GPU code to take the hash, compute the XYZ location, and then put it in place, and then rendered it. And this is essentially real time. So streaming the data in real time at around 1.5 gigabytes per second. This was SSDs in a database server and the GPU all integrated in one system, just to show that we can pretty much max out the I/O bandwidths in such a system, even when we have the data in a database.
What are you showing there?
So this is basically putting in 3 layers of particles, and they are moving in the velocity field of the turbulent flow, but it is coming in dynamically from the database as the motion is actually integrated. So we are able to essentially keep up with the data flow through the database, even though the data is not optimally organized. But the other proof of concept was that here the visualization was integrated with the data store. So there was no network in between, but it was the backplane of the server. Okay, so cosmology. So 2005, the state of the art was the millennium, 10 to the 10th particles, and produced 30 terabytes of data. All that data went onto a tape robot in Garching and pretty much never left. And so what made the difference is that Gerard Lamson took the Sloan archive framework and modified it to actually accommodate the galaxies derived from the semi-analytic galaxy formation and the halo catalogs and put it into a relational database. So basically, one can now in this database track merging history of halos, etc., and realistic distribution of galaxy types. However, the world has changed since. We have now simulations with almost 1 trillion particles. I think Joe showed the table of all the spectrum. Almost 1 petabyte of output, many of these. And it is clear that people want to use the database, but still many people who are in the wider astronomy community are still using the Millennium. And I think Piers talked about this, that because it's easy. Because it's easy and it became a reference. So everybody is now comparing against this. So how can we keep up with the data sizes? First of all, so we did spatial queries. It is very clear for a lot of things, and one can use the space filling curves. So once we started to see this pattern, so Tamás Budavári wrote a nice library, which is now used both for the turbulence database and the Millennium. So we published it in the SSDBM with Gerard. And the nice thing about it is the library has a generic interface to space filling curves, and we can drop in basically any implementation. So we have a little plugin module for different space filling curves, and the rest of the library works. And we have search solids, but even light cones, which have the ability to go back and look back time. So as we intersect basically the replicated periodic boundary condition volumes. Okay, and in the Millennium, so basically, what was really remarkable, Richard was there in December. There was a 3-day workshop in Garching about the usages of the Millennium database. So on the Millennium database, there are 600 registered users at that time, 17 million queries, 287 billion rows, and I think about 1,200 refereed papers written on the database over 7 years. And in this workshop, there were 3 days, 50 people who were all talking about innovative uses of the database. And it was, I think I learned an incredible amount during that meeting. Partly that people are not happy. They want to do much more now with the database. So that basically people play the database like a musical instrument. It was really remarkable how well people adapted. And they started to do a bunch of things that the database was not really designed to do. That was my lesson. And so what can we do to enable all these things? And what were the things? Okay, how can we go to petabytes, trillion particles, tracking actually. So far the database only had the halos, subhalos, and galaxies in it. How could we actually also track the dark matter that came up and up again? Where is the data located? How does it get there? How does it get, say, from the Garching Supercomputer Center over to the database servers? It is even within an institution, this is not an easy task, given all the firewalls and DMZs. There is an increased emphasis on value-added on-demand services. So some of these are, so I kind of put it into a couple of categories. Some of them are localized, SCDs. A lot of these are pre-computed. So you can generate now SCDs, semi-analytic models, star formation histories, and so on. And you can also take a subvolume and resimulate. But people now want to do this on the fly. They want to change the parameters of the semi-analytic galaxy formations, and it's a 70-dimensional manifold. So there's a lot of space there. What do we do with it? Certainly we can't allow this, even on the Millennium scale right now, to redo the whole simulation, but one could take, for example, a light cone and allow people to play with different scenarios. Anyway, from excess pattern point of view, these are all localized, generally a relatively small area around the halo. Then there are the rendering related problems. So there are the visualizations, how to make a movie, and then the lensing and ray tracing. And essentially, these are all related to rendering problems, where we have a 3-dimensional distribution, complex distribution, and eventually we want to project it down to a 2D virtual screen. Even in lensing, the way we do the lensing today is that we take the masses in slabs and we project down onto sheets, and then use basically the projected mass density as a refractive index and scatter the light rays from the background. So this is 2 ray tracing problems, basically. First is rendering onto the mass sheets and then scattering the light rays. Dark matter annihilation or building the light cones. Oh God, okay. And there are the global analytics. How do we do kind of things over the whole volume, which is kind of the traditional supercomputer patterns. There are then the data representations. How do we do particles versus hydro particle tracking in dark matter, aggregates, covariances, and so on. So there's the Milky Way Laboratory as another example. So we did get a CDI proposal with Piero and Rosie and Joe Silk. So this is based on the Silver River that was done in collaboration with Doug and Joachim. Essentially, the idea is to take lots and lots of snapshots and also try some immersive experiments in this so that we can, for example, put in an external dwarf galaxy and see how it gets disrupted in the time-dependent potential, or how can we actually do on-the-fly dark matter annihilation computations. This shows, for example, one experiment that one of my students did. Originally, Mike Coolen generated a similar image on the Via Lactea 2 simulation in 8 hours to render basically the dark matter annihilation. We rewrote it in OpenGL using point sprites. And basically now it runs in 24 seconds on a run-of-the-mill graphics card, which enables us to do experiments to change the cross-section. So simple annihilation, then a 1/v correction to the cross-section, 1/v squared, or what would be just a decaying dark matter. And we can do these experiments in seconds. So this means that we can explore a huge parameter space. It also means that we can go to much larger particle counts. Indra is an experiment we are trying to do that it's only a gigaparsec box with 1 billion particles, but we are in the process of running 512 realizations to build an engine where we can do essentially ensemble averages over large volumes. And this is dark matter only, but kind of going the opposite direction. Instead of generating the world's largest simulation, we are trying to generate basically a service where you can play with one simulation and then replicate it 512 times over and get the average. Okay, so challenge is how can we build a system? And basically, where should the data be stored? Premise number one, it shouldn't be at the supercomputers because the storage is just too expensive there. Posterior analysis must be still on top of the data, so we have to have enough compute on top of it. And we need, of course, high bandwidths. The databases are a good model, but are they scalable? And generally, the myth was that they are not. And Google is building databases which contain 100,000 nodes and span the whole globe. And so it is possible to build scalable databases. It is just not easy. Anyway, let's go to and these are the trade-offs. So I think, first of all, right now we are mostly stuck with the storage and the cost. And after that comes everything else secondary. And summary, so I'm finished. So Millennium is the prime showcase of how to use the simulations as a numerical laboratory. The community is really using it extremely well. There are emerging challenges, partly in the size, in wanting extremely sophisticated value-added services, and so we need a coherent strategy to go up one level, because it's not incremental. We can't do just a little bit more what we have been doing. The biggest challenge is that it would be nice to figure out a way if we could write directly from the simulations that's a file that is directly readable by the database. We can get rid of this stupid loading process. And there are some possibilities, so Gerard and I are working on a scheme to do this. It is not just about storage, but integrating access and data access and computation in a clever way. And basically, it's neither a database server problem, people already passed that point, but it is not a supercomputer problem either, because the supercomputer architectures today don't quite have the I/O bandwidth to have the data accesses that we need for this analysis. It's kind of in between these two. But it would, if we can do this, it would tremendously increase the community buy-in of such simulations. And I think scaling to exabyte today would be a challenge, but I think we can do petabytes. So we are at the point when we are starting to do petabytes. Thank you.